Now, I will explain the operation and how to sketch voltage and current waveforms of the half-wave rectifier. Principally, only one diode will turn on at one time. To know the switching sequence of these diodes, we will refer to the potential value of the anode terminal of these diodes. For your information, the potential value of the anode terminals is directly proportional to the amplitude value of the phase voltages. Typically, the diode with the highest potential of the anode terminal will start the current conduction. Before we analyze the waveforms, I will remove the negative half cycles to make our analysis easier. Now, let's start at omega t equal to 0. At this angle, we can see the amplitude of the blue voltage is higher than the red voltage. Therefore, diode D3 will turn on. This diode will conduct the blue line current until this intersection point. At this point, the diode will stop the current conduction because the amplitude of the blue voltage is equal to the red voltage. And when you analyze the circuit, you can see that the blue line current is also the output current of the rectifier. And the wave shape of this output current is following the wave shape of the output voltage waveform with a smaller amplitude value. And when you refer to the second equation, you can see that the output voltage waveform is following the wave shape of the blue voltage waveform. Based on these equations, you can sketch the blue current waveform, the output current waveform, and the output voltage waveform as follows. Next, we will focus on this intersection point. After this point, we can see the amplitude of the red voltage increases and higher than the blue voltage. Therefore, diode D1 will turn on. And this diode will conduct the red line current until the next intersection point. By analyzing the equivalent circuit, we can see from the first equation that the red line current is also the output current of the rectifier. And the wave shape of the output current is following the output voltage waveform with a smaller amplitude value. And based on the second equation, the wave shape of the output voltage waveform is also following the wave shape of the red voltage waveform. Therefore, we can sketch the red current, output current, and the output voltage waveforms as follows. Subsequently, after the second intersection point, we can see the yellow voltage has the highest amplitude value. Therefore, diode D2 will turn on until the next intersection point. After the last intersection point, we can see that the blue voltage has the highest amplitude value. Therefore, diode D3 will turn on once again. Based on these conduction ranges and the previous circuit analysis, therefore, we can sketch the line currents, output current, and output voltage waveforms as follows. Now, give your attention to the wave shape of the output voltage waveform. Based on the graph, we can see that the output voltage waveform consists of 3 voltage pulses. Because of that, the half-wave rectifier is also known as a 3-pulse rectifier. Next, please focus on these conduction ranges. From these levels, we can see that the output current of the rectifier commutes from one diode to another diode at every intersection point. Therefore, these red vertical lines are referring to the commutation lines of the half-wave rectifier. Other than that, based on the ranges, we can calculate the conduction angle of each diode. Based on the labels, the conduction angle of each diode is 120 degrees or equivalent to 1/3 of a complete cycle of the half-wave rectifier operation.